Mathematicians look for patterns in the world around them. Then they translate them into algebra. Now we already did this with our lines and our slope. When we found a straight line, we figured out we could calculate the slope and write it in an equation, y equals mx plus b. Well, we're going to do the same thing with these interesting curves called parabolas. But first, we need to find them. So let's go on a parabola hunt. That beautiful arcing shape can be found in all kinds of places. Favorite roller coaster, even in the beam of a flashlight. And of course, if we're hungry, at our favorite fast food restaurant. Also, they can be found in satellite dishes. They can be found in toys. They can be found in old architecture, and even in the sky as a rainbow, and you may even have them on right now. Some places it would be hard to find, but check out the tiles in this roof. And then, of course, parabolas are very important in video games. Who knew parabolas could be found somewhere scary? Well, I say we call this hunt over because the parabola hunt became a bear hunt. So now let's look at the geometric definition. First, let's figure out what a geometric definition is. Let's look at circles. We're pretty familiar with circles. So a circle is a closed plane curve consisting of all points at a given distance from a point inside of it. So if we look at this picture, we have a central point C, and that given distance x goes all the way around that circle. It's the same distance. We actually call that the radius. But that's a geometric definition for a circle. So now let's look at a parabola. A parabola is a curve in a plane where any point is at an equal distance from both a given point and a given straight line. So we have a point and a line that we're looking at. The point is called the focus and the line is called the directrix. Now this line doesn't belong to the parabola, it just helps us define the definition. So if we look at the focus, that point right there, that point F, and we look at the line or the directrix, that shows that there's equal distance between those two. So if we take it from the focus to the parabola, to a point on the parabola, and from the directrix to that parabola, that's the same distance. If that distance were 3 from the focus to the parabola, from the directrix to the parabola would also be 3. So let's take a look at an applet that shows the parabola. The parabola is in red right here. So this is the parabola. And here's a point on the parabola. Now, if we look at it, that's the equation right there. We're not going to worry so much about that now, but here's the focus. So this distance from the focus to a point on the parabola is the same as the distance from the directrix, a line down here, and it even gives us the equation of the line right here. We don't need to worry so much about that now, but it's the same distance from the focus to the point on the parabola as from the directrix to that point on the parabola. So if we have a line and a point, and we look at all those points where that distance is equal, so that distance is equal to that distance, and as we move it along this parabola, the focus distance and the directrix distance stays the same, so it's exactly the same. So that's how we define geometrically what a parabola is. Now this was created using a program called GeoGebra, and GeoGebra is a free program you can use to make these kind of visual programs. Here's something else that's kind of cool about a parabola. If you take a point on there, that focus point, and you point a light source at it, see how it's hitting it in different ways right there? It all comes back in a straight line. And that's actually how headlights are designed. So if you look at the mirror behind that headlight, you can see it's shaped like a parabola. And so when the light bounces off of that, it goes out in a straight line so that you can see while you're driving. Let's look at some of the words we use to describe parabolas. Mathematics is like another language, and you need to know the vocabulary in order to communicate with other mathematicians. So if we look at our parabola, the axis of symmetry is the line that divides the parabola into two halves that when you fold them, they are the same on both sides. We already talked about the focus and the directrix, but along that axis of symmetry, you will also find what's called the vertex, and that's either the lowest or the highest point in the parabola, depending on which way it's facing. if you look at this parabola, you have places where it crosses the x-axis. Those are called x-intercepts. Where the parabola crosses the y-axis, that's called the y-intercept. Now, the x-intercepts have lots of personality, and we use those a lot. So they actually have more than one word we can use to describe them. So x-intercepts can also be called roots or zeros. So you can call them the x-intercepts or the roots of the parabola or the zeros of the parabola. And it's only for the x-intercepts. The y-intercepts are not like that. So here we have lots of different things here. We have the axis of symmetry, which is actually a line. It doesn't belong to the parabola, but that's the axis of symmetry. And that line will have an equation. X equals when the parabola looks like this. So this is x equals -2. That's my axis of symmetry where you fold the parabola in half. I also have my x-intercepts, which I'm calling roots. And in this case, I have a negative root and a positive root. I also have my y-intercept here, and I've marked it as a coordinate point, and my vertex. In this case, it's the minimum. Okay, so let's take a look at a different kind of parabola. This is upside down than the others, but it still has the same anatomy. So right here, we've got the vertex. The vertex is at 2, 3. And if we look over to the y-axis over here, we can see that our y-intercept is at 0, 1. So that's the y-intercept for this parabola. And we have over here at -0.4, 0, an x-intercept, or we could say a 0, or we could say a root. And then over here on the right, we have another x-intercept, or a 0, or a root. We could call those any of those names, and that one is at 4.4, 0. So notice the y is 0 on our x-intercept. And that makes sense because at the x-axis, we haven't gone up or down. Now let's go ahead and draw our axis of symmetry where we can fold the parabola in half. And normally we represent this as a dotted line because it doesn't actually belong to the parabola. And we can write the equation for this line. Now when a parabola is faced like this, and it's got up or down, and it's got some x-intercepts right here and their y-intercept, that equation is going to be a vertical line. And the equation of this line actually takes part of the vertex, so the x-coordinate of the vertex, and that's at x equals 2. X is always equal to 2 on this line. Now remember, this line just shows where the parabola can be divided in half. And if you notice, our x-intercepts are equal distance away from our axis of symmetry. Okay, so let's figure out now how to use algebra to represent parabolas. So if we have a parabola, looks like this, let's go ahead and put it on a grid to really dissect what the equation's going to look like. And let's look at several points on here. Now, I could take any kind of parabola. I chose this one because it's symmetrical about that y-axis. And so I can choose some points here. Let's go ahead and make a t-chart and look at the different points that are on this parabola and see if we can come up with an equation. So our first point is actually the origin, 0, 0. So when x is equal to 0 on our graph of this parabola, y is also equal to 0. So it's the same. So maybe it's x is equal to y, although that creates a line. But let's look at this point. So if we have the point 1, the point 1, 1 is also on our graph. So when x equals 1, y also equals 1. So maybe we have x is equal to y, but let's look at a few more points and see if we can disprove this. Let's look at this point right here. So when x equals 2, y is equal to, well, it's not 2, 4. So this is the coordinate point 2, 4. So when x is equal to 2, y is equal to 4. Well, x equals y, that's obviously not going to work out. That is a line, not a parabola. Let's look at a few more values on here. Let's just go ahead and look at -1. So when x is equal to -1, on my graph, y is equal to +1. So that's another coordinate point. That's interesting. So I put in a negative value and I got out a positive value. Well, let's look at this one. -2 and then y is equal to 4, so negative 2 comma 4. Very interesting. I see that I'm getting all positive values, and it's looking like I have this bit of symmetry. So let me just highlight what happens. So we have when x equals 2, y equals 4, but when x equals negative 2, y also equals 4. So somehow we're doing something to x such that our y values are always positive and symmetrical. So let's think about what we could use as an equation to represent this. Maybe let's try a couple more values. What about 3? Well, when x is equal to 3, y is equal to 9. So let's try a negative 3. Well, look, I can already tell it's gone up 9. So when x equals negative 3, y equals 9. And that gives me another relationship to look at. So I know 3 and 9 are related. I know 9 is a square number. That means if I multiply 3 by itself, I'm going to get 9. I also know that 4 is a square number, as is 1. So it looks like I'm squaring x to get y. So 1 squared gives me 1, 2 squared gives me 4, negative 1 squared gives me 1, and negative 2 squared gives me 4. 3 squared gives me 9, and negative 3 squared gives me 9 as well. So it looks like my equation is going to be take x and square it, and that's what y is equal to. So y equals x squared. Now we have a way to represent a parabola. So we can take this equation and we can manipulate a little bit to move the parabola around. Pretty amazing that we can find a mathematical equation that describes the slinky. Not only does it have a cool little song, but also can be represented with algebra.
One walks downstairs alone or in pairs and makes a slinkity sound. A spring, a marvelous thing. Everyone knows it's slinky. Everyone knows it's slinky.
Slinky in metal and plastic.